Hello, dear participants of Combinatorial Optimization at Work. We are very pleased that the summer school is taking place online in this format, despite all the restrictions imposed by the COVID-19 pandemic, and that we have the opportunity to give you an insight into the application of optimization methods at SAP. I am Sabine Seelenmeyer. After my PhD in polymer chemistry at the Kißler Institute of Technology, I started a postdoctoral position in the chemical industry. Since 2001, I've been responsible for various roles and functions in software development at SAP in Walldorf. For 10 years now, I've been leading the development area for mathematical optimization globally.
Hello, my name is Kißler. I gained my master's degree in mathematics at the University of Heidelberg. For 4 years now, I'm working in Sabine's team as an expert for transportation and warehouse planning procedures. Over the past few months, the COVID-19 pandemic has shown us how important functioning logistics are for each and every one of us. You surely remember the empty shelves in the supermarket on your search for toilet paper or noodles, whose demand could not be met because of panic buying. We had to go to several supermarkets to find a kilogram of flour, and even online, these goods were no longer available. This bottleneck situation shows us our dependency of resilient, meaning robust and flexible supply chains for food and consumer goods. We will therefore now discuss how optimization and artificial intelligence methods are used today and will be used in the future for the planning of multimodal logistics. Logistics is the planning, execution, and control of the procurement, movement, and stationing of personal, material, and other resources to achieve the objectives of campaign, plan, project, or strategy. It may be defined as the management of inventory in motion and at rest. Logistics management software therefore answers questions like, where do I get the needed resources from? How are the resources transported? And where do I want the resources to be and at which time? Logistics planning plays an important role in this context. If you assume that the core competence of a company to survive in the market is to produce a high output with a limited number of resources, or to produce a certain output at minimum cost as a dual problem, then optimization methods and algorithms are needed to ensure the survival of the company. The software that our team develops is used in all applications that industrial and logistics companies worldwide use to plan and optimize their business. This covers large parts of the value chain, from production planning and intralogistics through transportation and warehouse planning to the optimized deployment of service technicians. To illustrate the dimension of the optimization challenges that we face, a logistics company or service provider plans and optimizes the entire delivery route of each individual parcel or container worldwide. With our software packages, 46 of the 50 largest logistics companies in the world optimize their entire portfolio of logistics services daily and in real time. In addition, 98 of the 100 largest manufacturing companies use our software for both external and internal logistics and for planning their production. The reality of the logistics business presents us with a number of mathematical and technological challenges that we face during the optimization software engineering process. In the real world, logistics itself is a complex business with many different business processes and industry-specific scenarios. This complexity is reflected in a large amount of business constraints and constantly growing data volumes that the optimization methods have to process. Scalability of the algorithm as well as high performance are therefore basic requirements for the optimization services. A high solution quality of the optimization results is expected, since the cost savings achieved by the corresponding process optimization are of essential importance for a company. Every percentage point counts for the increase of a company's margin. And data consistency is one of the absolutely necessary prerequisites for achieving this high solution quality. The optimization methods must also be legally compliant. Data compliance refers to any regulations that a business must follow in order to ensure the sensitive digital assets it possesses are guarded against loss, theft, and misuse. These may be industry standards, state or federal level laws, or even supranational regulations such as GDPR. As planning is a business critical process, permanent availability of the optimization services must be guaranteed. The optimization software engineering process usually starts with the understanding of the business process and its requirements to be modeled. Let's look at some of the real-world requirements in the area of route planning, scheduling, and load planning. Business hours. It is a typical requirement in route planning that shops have opening hours. Trucks should arrive during these time frames at the yard of the shop or supermarket. Traffic patterns. When planning routes, traffic jams that typically occur in the morning and the evening should be avoided if possible. Truck driver availability and fees. A driver's fee is depending on the driver's activities, like driving, waiting at a border, and breaks. The resulting different operational costs must be reflected in the objective function. Additionally, there are country-specific legal requirements that define a driver's rest times. These are hard constraints for the driver's availability. Package shape and weight. If truck load is not evenly distributed, the truck can tip over. Load planning of a truck must therefore take into account the weight and center of gravity of the loaded packages and the allowed axle weights. The shape of the packaging, for instance pallets or tubes, must also be taken into consideration if you want to achieve the optimal tightest packing. A planning solution can only bring valuable decision support to a planner if it solves his concrete planning problem. Even optimal planning solutions are worthless if they are not feasible in real life. The art of modeling is now to map the real-world business process into a mathematical model. The analysis and precise understanding of the business requirements is a key to achieve this goal. During this concept phase, it is decided whether a business requirement is modeled as a hard or soft constraint, whether it can already be supported in the existing model, or whether a new development is needed. The correct identification and modeling of business requirements is a continuous dialogue between planner and modeler. As soon as the requirements are understood, we can start modeling the planning problem as an optimization problem. This step can be arbitrarily complex, as a planning problem in logistics may contain several classic optimization problems whose solutions depend on each other. One example for a planning problem is the route planning in a multimodal network. The goal is to find the optimal routes from plants to warehouses via transshipment locations for a large amount of goods. The decision how the material flows within this network can be seen as a network flow problem. The planning of the route starting or ending at one transshipment location can be defined as a vehicle routing problem. Another classic optimization problem that is included in the route planning problem is the scheduling problem. The availability and capacity of handling resources like forklifts or port cranes need to be optimally utilized. Bin packing problems occur in the context of truck loading optimization. It is obvious that the solutions of these problems depend on each other. These dependencies significantly increase the difficulty of finding a suitable algorithm to solve the defined optimization problem. Exhaustive research work, expertise, and continuous development of algorithms are needed for this crucial step, and there are more criteria that need to be taken into consideration. Since we deliver the optimization services as standard software, we have to ensure and guarantee different product and quality standards for the optimization algorithms, which are expected by our customers. Compliance with these standards often lead to compromises where it's not only about finding the optimal solution. Performance. The response rate of the algorithm has to be short, independent of the size of the planning problem. A further standard is the explainability of the algorithm. Users often don't trust the result if it contradicts their personal manual planning experience. It is therefore expected that the software provides explanations why a certain solution was chosen and another wasn't, and that the behavior of the algorithm is documented. Algorithm robustness. If two problems are similar, for example in route planning, some additional goods need to be transported. Then the provided result should also be similar. In the case of transport planning of multimodal networks, meta heuristics heavily using local search procedures have proven to be very successful in meeting these requirements. On the other hand, solvers for linear programs and mixed integer linear programs are successfully used for deployment planning within supply networks or for supporting the selection of suitable carriers for given planned shipments. In the end, the proof of concept of the modeling and of the chosen algorithm is always the test in a concrete, real business environment. Changing and new business processes in logistics as well as new technologies therefore always imply that model and algorithms have to be constantly rethought and adapted. We would now like to go into these in more detail.
Logistics has developed significantly over the last decade. In the past, supply chains were static and were optimized along rigid constraints. In the future, we will talk about demand-driven supply networks that span different modes of transport. In other words, the complexity of logistics has exploded in the last decade. We are currently in the transition from static supply chains that are optimized under fixed boundary conditions to highly flexible networks that react even more promptly and quickly to changing customer demands and external events. Whereas optimization has so far been based on a global objective function, in the future these supply networks will no longer be able to be represented by a global model. Instead, there will be a large number of decentralized plans that must be optimally coordinated at a higher level. There's a great need for research to enable this flexibility and mutability of production and logistics systems, but also their objects, such as drones, autonomous vehicles, or forklifts, and to integrate them adequately into existing supply landscapes. Technologies of the fourth industrial revolution, such as Industrial Internet of Things, create a new dimension of real-time visibility into the supply chain down to the level of the individual package. The tools of Industry 4.0 can be applied to objects in the logistics, such as trucks, forklifts, pallets, or packages. The digital twin of these objects makes it possible to collect and analyze data in a structured way during their life cycle. Suitable standards for data exchange then allow these real-time data to be integrated into the planning algorithms with a high level of granularity. This will significantly improve the optimization of logistics, for instance, to significantly reduce empty runs in the future. So far, classical mathematical optimization methods have dominated. These are gradually being supplemented and enriched by further artificial intelligence methods and simulation. Let me explain this. Current optimization methods are based on classical mathematical methods, like linear optimization, pure integer and mixed integer linear optimization. These methods are enriched with forecasts and empirical values from the past, such as sales figures or transport intensities, in order to develop optimization models that maximize a complex objective function under a variety of boundary conditions. Uncertainties exist for these heuristic parameters of the models, which are compensated by safety margins and flexibility buffers. This leads to unused overcapacities and inventories. In the future, artificial intelligence tools that access the data of digital twins, for instance trucks and containers, and extract patterns from historical planning data will significantly improve the quality of these prognosis and experience parameters. Three obvious examples that we are currently working on are deep learning extraction of planning costs for transportation planning, deep learning forecasts for congestion times and travel times to optimize the route and the delivery times, deep learning of loading meters of recurrent products for the optimization of the loading space of trucks or containers. The complexity of the future logistic networks requires a paradigm shift away from the deterministic truth towards stochastic probabilities in the planning and control of logistics processes. Simulation models will become indispensable for planning in the future in order to understand the quasi-stochastic behavior of logistic networks and to optimize their design. Logistics networks are already overcoming company boundaries in the cooperation along a value-added chain and will increasingly be handled via digital platforms in the future. The logistics industry is highly differentiated in its interaction with its customers. Supply chains and networks span a multitude of company boundaries from pre-products to Tier 1 suppliers, OEMs and end customers. In the future, digital platforms will coordinate the processing of logistics tasks via the value-added network. Data will thus be stored in these platforms. These digital logistics platforms will allow the use of artificial intelligence methods for pattern recognition and process optimization. The platform will merge the data and thus allow meaningful pattern recognition. Future intelligent logistics solutions will have to address the social, technical and economic challenges of our century. 78% of the global economy uses SAP software for its processes. Consequently, SAP and SAP optimization have a massive impact on making business processes more sustainable and climate-friendly, and supporting other UN-sponsored sustainable development goals. The next topics we are focusing on are decarbonization and enabling a transition to climate-neutral logistics solutions by including carbon dioxide emissions in the objective function. Relieving the burden on the infrastructure by optimizing capacity utilization to avoid empty runs. Typically, 35% of the runs is currently empty. Reduction of the microparticle emissions in cities and metropolitan areas by optimizing the model mix. Using of autonomous vehicles for both the last mile and to optimize driving times throughout the day. Developing a supply chain management for the future circular economy. Enablement of a resilient supply chain. Given of the experience of the last month, our customers have reprioritized their planning procedures to strengthen the resilience of their supply chain. And last but not least, optimization on quantum computers. Just recently, we started to contribute to the initiative of the German federal government to establish a quantum computing ecosystem in Germany. Thank you very much for your attention. We are looking forward to your questions, which we will gladly answer in the planned Q&A sessions. See you!